Hey everybody. So today we're going to now start talking about series. We've been talking about sequences, geometric and arithmetic sequences, and we talked about some improper integrals as well, about whether or not they converge or diverge. Now we're going to talk about power series. And power series in terms of numbers, series of numbers, and functions as well. So grab your notebook. We're going to be putting a few things on note cards, so if you don't do it now, we'll do it next time that we're in class for some reminders. We're going to start building family, a set of functions that are going to be some of our base functions that we're going to be working with. And as always, please, please, please pause me, or if I ask you to try something, pause the video and try it on your own, but make sure that you go back and rewind and ask questions. And also, as we enter into this new unit, homework assignments that I'm going to assign, some practice problems, you really, really want to do them. They're not really optional because, or else if you don't put practice some in, then you're not going to know the types of questions to ask. All right, with that said, this is super interesting. Might take a little while to get through some of this, but I think it's pretty easily digestible and frankly kind of interesting. So let's take a look. All right, so let's start out here with 1 squared unit. Let's just set a foundation for what a series is. So if I break that into a half, I'm going to take the value of a half, and then I'm going to break that half in half and a quarter. And so I want to start adding these areas together and having it and add that, having it and add that. Well, if I keep adding this over and over and over again, what will the sum ultimately be? If I could do this infinitely number of times, well, it's going to approach 1, the actual area of the entire square itself. So this is an example of an infinite series where we're going to be adding up an infinite number of terms to see whether or not it approaches a particular value or not. And in this case, it does. Now, this is a pretty unique series where I was having everything. So obviously we're looking at some sort of a geometric series. And again, yes, this series converges to a limit of 1. But again, many series do not. If I just take the simple series of 1, a half, plus a third, plus a fourth, plus a fifth, that series does not converge. That just keeps getting bigger and bigger and diverges. So we're going to examine here why some things converge and why some things don't, and look for some common series that do converge. So a little bit about notation. So here I have a series. So if you're asking the difference between a series and a sequence, you could say it's as simple as sequences are just a list of numbers with commas in between them. But a series is where we're going to be summing up those numbers. And we're going to be talking about infinite series. We're going to be talking about adding up an infinite number of numbers to see whether or not it converges or diverges. So we have our summation notation here for my terms. So all of these subscripts we use to identify the terms in the series. A sub n is the nth term in the series. Now, partial sums means that, well, obviously we can't sum up an infinite number of terms, but what if we start looking for patterns? So what if we take the first partial sum, which frankly is just the first term? That doesn't tell me much. But the second partial sum is where I add the first 2 terms to see what that adds up. Well, that might get me a little closer to an idea of what's going to happen. Or the third partial sum, or the nth partial sum. We're going to take an n number of terms. This is just the general expression. Obviously, we're going to want n to go to infinity to see whether or not the series converges or diverges. And if that nth partial sum does have a limit as n approaches infinity, it converges. Now, we may not know what it converges to, but we will know that it converges. So here's the example that we looked at originally. So a geometric series. A geometric series is just like a geometric sequence where we're multiplying by a common ratio. So you can see each term in this series is just multiplied by additional r value. So times r, times r, times r. So ultimately, the expression then for the sum is n equals 1 to infinity of a times r to the n minus 1. If n equals 1, that would be my first term going in, and I have an exponent of 0. R to the 0 times a is just a. That's why we're seeing just an a here as my first term if I let n equals 1. You might see other expressions here, but to get with different exponents or different starting values, remember the starting term in the series is always whatever this lower value is substituted in whatever the value that generates. We'll talk about that as time moves on. And this geometric series, and I'll show it here a little quick proof in a second, but we know that geometric series converge if the common ratio is somewhere between 1 and -1, or the absolute value of r is less than 1. So this is a domain of -1 to 1, not inclusive. And it'll converge to a over 1 minus r, a being the first term and r being the common ratio. A simple formula that we're going to use a lot. This concept we actually could have talked about in an earlier math course. There's no real calculus happening just yet. But if r was greater than or equal to 1, it's going to diverge. And hopefully that makes sense, because if you keep multiplying by a value that's bigger than 1, well, then the terms are going to start to get bigger and bigger. So therefore, the sum is going to have to diverge. It's only when I get those proper fractions between 1 and -1 that I'm going to wind up converging. If r equals 1, then we're just going to keep multiplying by 1, by 1, by 1, by 1, and I would just have a's values just summed up an infinite number of times, which would approach infinity. So this is what's called the interval of convergence. If r is somewhere between 1 and -1, not inclusive, that geometric series will converge, and it will converge to a value of a over 1 minus r. So we're going to want to make sure that we get this onto a note card to remind ourselves. People studying at home, I will help you put that on next time that I see you in class. So here's a quick little proof. So here's a little proof of, now this is using a sub 0, but still talk about our first term at a, and I equals 1 to infinity. So here's me just writing out the first couple terms. So that's the first couple terms of this series. Well, all of those terms I can factor out in r. If you factor out that r, you're going to be left with then this term a sub 0 r to the -1st, and then all the rest of these terms are the actual series itself. So plus s. Now if I do a little bit of algebra, combine some like terms, and factor, we can see we get my a sub 0, my first term, over 1 minus r. So it's a pretty easy proof to see. So let's look at a couple examples. Now remember, not all series are geometric. Is this geometric? Yeah, I think so. I'm multiplying by 1/10 every single time. And since I'm multiplying by 1/10 every single time, 1/10 is within the interval of convergence between -1 and 1, so this will converge. But frankly, we could look at this in terms of decimals. 3/10, 300, 3,000. And adding all those up, you can see what that's going to add up to. It's just going to add up to 0.3 repeat. So it comes out to converge to a third. Well, let's look at it with our formula. So a was 3/10 over 1 minus r. R was 1/10. And again, 1/10 is within the interval of convergence. So therefore, I can use this formula to find what it converges to. And doing some simplifying and some reciprocating. And sure enough, get 1/3. So the formula pans out. Let's look at another one. So again, might want to pause me here and think about what we just did, see if it converges, and if so, what does it converge to? Well, this is geometric. A is 1, r is -1/2, and -1/2 is within the interval of convergence, so therefore it will converge. And simplifying this expression gives me 2/3. These fractions summed up will sum up infinitely to a sum of 2/3. Pretty nice and easy. So we might not always see the sequence or series written out with separate terms. We might see it in its summation notation. So this is an infinite geometric series, if you can't tell, because each term is going to be multiplied by a half. So I'm going to take a half multiplied over and over and over again, depending upon what n is. Now be careful, this term out in front isn't always necessarily a, but in this case it is my first term, because if I let n equals 1, 1 minus 1 is 0, and a half to the 0 power is just 1. So this does turn out to be the first term, so be careful. So 1/2 is within the interval of convergence, so therefore I can get its sum, and it sums up to 6. Now again, what I'm going to encourage you also to do is that if you see this in summation notation form, you might want to actually write out the terms themselves, just to kind of see what's going on. So I know my first term would be 3, and then I'm multiplying by a half every single time. So then that would be 3/2. Oops, trying to write with a pen here, it's not easy. And then multiplying by a half, so then 3/4. And And so we can start to see what my series is going to start to look like, but that's eventually going to add up to my 6. So what about this one? Is this going to converge or diverge? Well, first of all, it is geometric. I can see I'm multiplying by 1/2 every time. And 1/2 is within the interval of convergence. But the question is, well, now it started at 3. Now, is that going to make a difference? No, it's not going to make a difference. It's just going to change what it converges to, because now in this case, my first term is 3/8. Because if I let n equals 3, 1/2 cubed is 1/8. So my first term is 3/8. So this formula would be 3/8 divided by 1 minus 1/2. And so convergence isn't affected by removal of a couple set of numbers. It's still going to converge, but it will converge to a different value. One thing to consider is that if the series does converge, then I know that the limit of the nth term has to be 0. The terms have to be getting smaller in order for it to possibly converge. But just because the terms get smaller or head towards 0, that's what my second statement's saying here, doesn't necessarily mean that the series converges. Think about that series, 1, 1/2, 1/3, 1/4, 1/5. Those terms got smaller, but that series, we haven't proved it, but that series does not converge. So if the series converges, then the limit of the nth term is 0. So this series converges. So this series I will know is converging, and we will talk about later why it is. It may look familiar here. It's 1/n squared. So therefore, my conclusion about that, if I was told that this series converges, I know that the limit of the nth term is approaching 0. The nth term is going to get smaller and smaller and smaller as n approaches infinity. Well, in this case, if the limit of the nth term is not 0, then the series diverges. Because I know if I let n equals 0 up to infinity, these terms are just going to get bigger and bigger and bigger and bigger. So since the nth term does not approach 0, I know it diverges. So this nth term test we can use to prove divergence. Very easy to prove divergence. It's difficult. You can't really say it converges just because it goes to 0. Hope that's making sense. So for this series, the limit goes to 0. This is my 1/2, 1/3, 1/4. That's this series. And I can't tell whether or not it converges or diverges. We're going to need some other tests, which we will learn in subsequent days. All right, so let's catch our breath here before we switch from numbers to functions. So what I'd like you to do is, can you pause the video here? Check to see if these series converge or diverge. And if they do converge, what do they converge to? So go ahead and pause and see what you get. All right, so this first series does look geometric. It looks like my R value is 1/4, and 1/4 is within the interval of convergence. So I know it's going to sum to 1 over, oops, it's going to be really sloppy, 1 minus 1/4. And so therefore, my sum of this infinite geometric series sums to 4/3. All right. The second one, was this geometric? Yeah, this is geometric. So I'm multiplying by -1/2 every time. Interval convergence is -1/2, or R is within the interval of convergence between -1 and 1. So I can set up A over 1 minus R. 10 over 1 minus -1/2. I got 20/3. So this infinite series sums to 20/3. What about this next one? Yeah, this is geometric, but what am I multiplying by every time? Well, you can always tell from that term, the base of that nth term, it's 2. So this series diverges. So this is not R is not within the interval of convergence. It's outside the range of -1 to 1. So therefore it diverges. And this last one would be hard to tell whether or not it's geometric or not. Remember, what you can always do is you can take terms in the series, which we were talking about sequences before, and divide them. If subsequent terms keep dividing by the same value, you are going to get a geometric series. And it looks like the interval of converge, R is √2/2. That's what we're multiplying by each time. That value is within the interval of convergence. So if you set up your formula, a over 1 minus r. I did that and then ultimately simplified, got rid of some fractions and stuff. And I got, ooh, this is so bad. So 2 over 1 minus the square root of 2. That's what that infinite sum came out to be. All right, that should be pretty easy. So that's dealing with the world of numbers and series of numbers and geometric series. Geometric series are going to be our best friends because we can tell when they converge if r is between -1 and 1, and I know what they converge to. So we love geometric series. Not all series will we be able to figure out what they converge to. So let's expand upon geometric series here. So let's take, and instead, here's my geometric series, just written a little bit differently. I'm starting out with 1 as my initial term, and I'm multiplying by r every single time. And you would see that that sums up to a over 1 minus r. Well, what we're going to do now is, instead of calling those r's, let's call them x's. So what am I looking at here? I am looking at an infinitely long polynomial function. There's an infinite number of terms in this polynomial function. And if I could write those infinite number of terms, I would get a graph that looks like 1 over 1 minus x. But it's not going to look like that entire graph, because remember where this came from. These came from geometric series that r had to stay between 1 and -1 to converge. So in this case, x is going to have to stay between 1 and -1 to converge. So we're going to put these, or this series, this infinitely long polynomial series, on our note card, but let's explore this a little bit more. Infinitely long polynomial on the left, and then I've got this function on the right. But again, it's not going to be the entire function as I add more terms. So here, let's just take a couple partial sums. This is the third partial sum, so the first 3 terms of this polynomial. And the red graph is my function that it seems to be summing to. Well, you can see between -1 and 1 on the interval of convergence, boy, they really look a lot alike. Now, yeah, they start to diverge a little bit towards the ends, but could I get maybe a better approximation? Yeah, by adding another term. If I add another term, then it seems to widen out and they seem to be getting closer, staying closer to each other for longer and longer. Now, let's just make sure we understand that how many points of intersection do we have here? We only have 1. Just that one point, that starting point, that center point, which we'll call the center of our interval of convergence. And then there's all the rest are not touching. So you almost want to call these like a tangent curve as opposed to a tangent line. It's a curve that really approximates the function, but in this case, within an interval from -1 to 1. Remember, x or r had to stay between -1 and 1. So the more terms that you add, the better the approximation is going to be just within the interval of convergence. Now we will see that there are other series that we can write with infinitely long polynomials that have open intervals of convergence. The more terms you add, the wider the interval of convergence would wind up being, or the wider that the two functions are going to look alike. And we'll see that in coming days. But this has a restricted interval of convergence. So this equation, this infinitely long polynomial, that is what's called a power series. This is a power series. Power series are polynomial functions that we use to approximate other functions. So again, the more terms that you add, the better that they're going to be approximations of each other within the interval of convergence. Outside of the interval of convergence, good grief, you can see how quickly they diverge. It goes shooting off right beyond -1. Over here on 1, it looks like they're staying kind of closer together, but definitely outside of the interval of convergence, they will diverge. So power series comes in 2 different forms. This is the form that we just saw, where we have coefficients. Now, my coefficient was 1 every single time for this particular function. But we'll have coefficients, and then we'll have x terms with powers, increasing powers. We might not have all of the powers. We'll see that in coming days. But this is where we're going to be centered at 0, x equals 0. Not all functions are centered at 0, so we can perform a little translation like we've done back in earlier courses. So we're just going to take x minus a, and that a value will then shift. So for instance, my other graph, if I wanted that last graph, but I wanted to use it maybe to approximate a value at 3 or 3.1, well, then I'm going to shift my function over to be centered at 3 and use it to approximate from there. So we have coefficients, they're constants. The center A, where my center is going to be, is a constant. Right? The first series is centered at 0, as I said, or at the origin. The others are going to be shifted left or right, depending upon what A is. And again, don't know if I've really made this clear, but the reason that we were doing this, I'm going to go back just real quick, is that we might not be able to approximate the red function. Now, in this case, it was 1 over 1 minus x. That's easy to get values on that function. But there are some functions that we don't know, like sine of x is really hard to approximate at all its values, e to the x and ln of x and all those transcendental functions. It might be easier to work with a polynomial function that approximates that function to then substitute values in. Remember, if you put values into polynomial functions, all you're doing is a whole bunch of multiplications and additions. That's easy to do. Trig functions, logarithmic functions, exponential functions, those operations are a little bit more difficult. So if I can convert difficult functions into polynomial functions, I can use those polynomial functions, what I like to call tangent curves, to approximate the function just like we did with tangent lines. So once we have a particular series, then I will be able to manipulate it to be other series as well. So we just dealt with 1 over 1 minus x. Well, what about 1 over 1 plus x? Well, it doesn't seem the same, but if you think about it carefully, this is still a geometric series, but I've changed r to negative x. So technically that's 1 over 1 minus negative x. So that means I'm multiplying by negative x every time. So we get this alternating series, plus, minus, plus, minus, plus, minus, plus, minus. So let me pause there. So if I wrote out this infinitely long polynomial here, it would approximate this graph, again, only between -1 and 1. So I could get that approximation. I could then multiply both sides of the equation by an x. So I get this infinitely long polynomial function. This infinitely long polynomial function, the more terms that I add, the more closely it's going to represent this function between -1 and 1 again. So we can manipulate these equations. This was a simple multiplication. This was a simple changing of the r value. Well, what about if I wanted to do this? Well, if I wanted to get this function and find this function, well, how are they related? It's as if I multiplied the original expression by, or if I squared this original expression. Yeah, I could think of it as squaring it. Well, be careful. If you try to square a polynomial function, remember what you got to do? You got to square the entire thing. Just think about a binomial like x plus y squared. That's going to be x plus y times x plus y. And you have to do all your distribution. I would have to do the massive amount of distribution to do this. It seems a little insane. But if you look really carefully, if I take the derivative of this given function using a power rule of differentiation, I get this other function. So that just means that this new function is simply a derivative of the first function, which means all I got to do is differentiate all the terms. So therefore, this new series of 1 over 1 minus x, the quantity squared, is simply 1 plus 2x plus 3x squared and so forth. All I had to do is take the derivative. So we can manipulate series even through differentiation. Well, if I can manipulate series through differentiation, I can also through anti-differentiation. So again, given this one series that I'm starting out with, 1 over 1 plus x, I would like to find the natural log of 1 plus x. If you think about it, well, that's just the antiderivative of 1 over 1 plus x. So what I would have to do is anti-differentiate. But what about that constant? What do I do about that constant? Well, let's just switch these to t values here for a second. And you'll see why here in a minute. Because, yeah, the constant came from that indefinite integral, but what if we write it as a definite integral from 0 to x on both sides? And so I anti-differentiate both sides. So I wanted to write the functions in terms of t's because I didn't want an x where I was going to put an x. And then start substituting in my upper, my lower limits. Obviously on the right, if I put 0 in to all those terms will go to 0. So I get this expression, and there it comes. So now we didn't have to worry about the c because I dealt with an indefinite integral. Or I dealt with a definite integral, sorry. So here, look at this. We can approximate a logarithmic function. Oh, that's so hard to find approximations for. Thank goodness we have calculators to do that. But we can also approximate it using this infinitely long polynomial function. Now, since this came from that original power series, from that geometric series, my interval of convergence is still staying between 1 and negative 1. The more terms you add to this polynomial, the closer it's going to look like the ln of 1 plus x just within the interval from negative 1 to 1. All right. So again, what we're now setting the stage for is to start looking at other transcendental functions like trig functions and exponential functions and things like that. Functions that are difficult to find approximations for just generally, obviously without our calculator. So, but if we can convert them into polynomial functions, that's just a bunch of adding and multiplying, which can easily be done. It's tedious, but it can be easily done depending upon the level of accuracy that we want. All right, definitely want to be practicing these problems. So make sure you're checking out my assignment and asking tons of questions as we continue through this series.